Click on diagram 1. What do you think this technician is investigating? Look at the meter and deduce an answer. The technician is trying to determine the magnetic flux density inside a remote location where magnetic field is present. The instrument used is called a Gauss meter or a Tesla meter. Click on diagram 2. The technician in this animation is using a clamp meter. The clamp of this instrument holds a thick cable. What do you think he is measuring? This technician is measuring electric current across a cable. An electromagnetic induction process is applied here. The instrument used is called a digital AC-DC clamped meter. These two investigations are the preamble to the study of Hall effect, which was discovered by Edwin Herbert Hall in the 19th century. Both test instruments used above apply Hall effect sensors or Hall generator to produce a reading in the meter. A better understanding of electric field, magnetic field, Lorentz force or magnetic force, and Hall effect will help instrument engineers and technicians get the most out of these instruments. Introduction. In this lesson, you will understand Hall effect by investigating the motion of charge carriers in an electric and magnetic field, observing the deflection of charge carriers in a current-carrying conductor when acted upon by a perpendicular magnetic field, derive the expression of Hall voltage, explain the significance of Hall effect for semiconductors, describe the uses of Hall effect. We are going to demonstrate the effect of a moving charge particle into an electric field. To understand Hall effect, the behavior of a charged particle in an electric field and magnetic field has to be investigated. Click the positive charge button to select the charge. Click the Start button to allow it to move with a uniform velocity inside the electric field. Predict the trajectory of the charge. Click the negative charge button and click the Start button to let it move with a uniform velocity inside the electrical field. Predict the trajectory of the charge. Answer: both the positive and the negative charge move in a parabolic path. The positive charge moves downwards and the negative upwards. A positive charged particle is moving with a uniform velocity of 2.5 times 10 to the power of 4 meters per second, perpendicular to the electric field E as shown above. A potential difference of 5,000 volts is applied to the plates. The plate separation D is 5 centimeters. We are going to animate the motion of a positively charged particle in an electric field. The magnetic field slider B is initially set as 0. Click the positive charge button and the Start button to observe the trajectory. Drag the B slider to 1 Tesla. Click the Start button to begin the animation. Calculate the values of magnetic force or Lorentz force and electric force acting on the charged particle. Click the Answer button to insert the values in the table. Repeat the process for 2, 3, 4, and 5 Tesla. Why did the charged particle move in a straight line when the magnetic field was 4 Tesla? Answer. The magnetic force balanced the electric force acting on the charged particle. The net force acting on the positive charged particle is 0. The term Lorentz force is used here to denote the magnetic force. Both the terms Lorentz and magnetic force is interchangeable. At 4 Tesla, the particle moved in a straight line. In this calculation, we will see that both the forces from the magnetic and electric field have created a zero net force. Click the Lorentz force button. Click the electric force button. Compare the results of these calculations. Summary. Electric force on a charged particle is given by Fe equals QE equals QV over D. The magnetic force on a charged particle, also known as the Lorentz force, is given by Fb equals BQV. We are going to investigate the force exerted on charge carriers in a metallic conductor placed in a perpendicular magnetic field. A thin sheet of gold foil will be used to simulate this animation. Let us look at a thin sheet of gold foil with width d and thickness t. In the experiment conducted by E. H. Hall in 1879, he used the same gold foil above with a width d of 10.0 millimeters. The thickness t is typically in the range of 0.5 millimeters to 1.0 millimeters. Introduce a current I into the foil. Click the current button. Click the Start button to observe the animation on how electric charge carriers flow in the absence of a magnetic field. Observe that although the direction of conventional current is shown, electrons flow in the opposite direction. The charge carriers are electrons and their drift velocity is indicated by Vd. Apply a magnetic field B perpendicular to the plate of the gold foil. Click the magnetic field B button. Click the Start button. Observe how electrons are deflected towards the left side of the conductor when a magnetic field is applied. Why does this effect happen? Answer. The applied magnetic field B produced a magnetic force on the moving electrons to deflect them in a circular path towards the left side of the foil. Can you predict the direction of the magnetic force acting on the charge carriers? Drag and drop the correct direction of the magnetic and electric force acting on the charge carriers and place it on the gold foil. As negative charges begin to accumulate on the left side of the conductor, electric force acting on charge carriers gradually begins to increase. Observe how the electric force vector on the charge carriers gradually increases until it reaches a maximum value. Reset the animation. Restart it by clicking on the Reset button, the Magnetic Field B button and the Start button. This time, observe again how the electric field vector begins to increase gradually. The accumulation of charges at the edge of the conductor increases until the electrostatic field set up by the charge separation balances the magnetic force on the carrier. In the animation above, magnetic field B is kept constant. Therefore, magnetic or Lorentz force acting on the charges is also a constant. The electrostatic field builds up from zero, thus increasing the electric force acting on the electrons. When an equilibrium condition is reached, electrons are no longer deflected towards the left. They move in a straight line. Normally, this equilibrium condition takes about a nanosecond to achieve. In our animation, we have slowed down the process to approximately 10 seconds to investigate microscopically the build-up to an equilibrium. Now, place a sensitive voltmeter across the gold foil. Can you think where the voltmeter should be connected? Click the voltmeter button to view where the voltmeter is connected. The value shown by the voltmeter is known as Hall voltage. Although the reading is very small, we will see later that when a semiconductor is used instead, the Hall voltage would have readings in the millivolt range. The direction of current flow through the voltmeter indicates the polarity of the charge carriers. In this case, charge carriers are electrons. Therefore, the electrostatic field resulting from charge separation has made the left side to be at a lower potential than the right side. Hall effect remained a laboratory curiosity because of the extremely low voltage produced then in 1879. With the development of certain semiconductors such as gallium arsenide and indium arsenide about 100 years later, relatively large Hall voltage can be produced. This led to the widespread use of Hall effect in science and industry that would revolutionize sensors development towards the third quarter of the 20th century. Summary. When a current-carrying conductor is placed in a magnetic field, a transverse voltage is generated in a direction perpendicular to both the current and magnetic field. The polarity of Hall voltage depends on the type of charge carriers in the conductor. When the electrostatic field set up by the charge separation balances the magnetic force on the carrier, Hall voltage is produced and can be measured. This observation is known as Hall effect.